Okay, so in order to make clear who is the guilty person for this lecture, this is an answer to a question of Professor Casciola at the last part of my first lecture. He was underlining, and I agree with him, that the presentation I was organizing for I was thinking for you was too abstract, and therefore I could have lost some of you in the discussion. So while reading the book of Piola and the book of Hamilton, I have copied the examples which these two scientists used for giving examples of their theory. So of course, I modified a little bit for presenting in a more general and in a more modern form, but the idea is there. Okay. By the way, these ideas are present in every model of physical phenomena, so you should try to extrapolate from these examples the features which hold in a more general setting. So even if now I start talking about two material particles, okay, which we can assume are interacting one with the other in a way which I indicate with a spring. They are subjected to external actions, okay, and they have a mass and a kinetic energy. Okay, so we are talking about a very simple system. However, some of the features of this example are in common with all other mechanical systems we can conceive, and I want to show you this example simply because I want to let you understand clearly what is internal work, what is external more, what is work, and how we can split work in at least in three terms: internal work, external work, and inertia. Okay, inertial part of work. So let us start with these two particles. We assume R1, R2, the tribal of coordinates characterizing the position of the first particle and the position of the second particle. Okay, so R1 is a tribal of real numbers, R2 is another tribal. The Lagrangian parameters for this system, if you introduce this mathematical model, are 6 real numbers. The Lagrangian velocity is v1 and v2 vector, so a vector made of 6 components. Okay, and we can conjecture, following Hamilton, that this system is moving under the action of external actions given by this ux, interacting one with the other, with this other potential. Okay, so given the way in which they interact one with the other, and given the way in which they are interacting with the external world, okay, we conjecture that the motion of these two particles is given by the minima of action functional built with this Lagrangian function. I do not want to hear the question, why? This is the mathematical model we want to use to try to predict what is going on. If you prefer the postulation based on forces, I will ask you why. So why you are assuming there is a force on a particle? What is a force? Okay? So the only proof that what we are telling is useful will be that we forecast the actual behavior of these two particles. I mean, we measure the motion of these two particles, and what we measure is predicted by our Lagrangian. Okay, so there is no other way for proving this. This is a standard process. Okay. Why I say that this is Hamilton conjecture? This is Hamilton conjecture because it is Hamilton who first understood that a suitable Lagrangian is very often kinetic energy minus potential energy. And he was the first one who recognized that potential energy can be split in internal potential energy and external potential energy. Okay? Now, I wanted to write two examples. For instance, but it is not the only one, you can assume that you have a true quadratic spring, and therefore the internal energy is given by this. Okay? This is a particular instance of internal energy. And you can have as a external energy, you can have, I am writing this because I want to write everything in vector components. So if you have a gravitational interaction, and if G is a vector which is minus a scalar times the vector E3, so you have chosen E3 in the direction of gravity, then you have a particular form of external energy which is given in the course of physics first year. In that form, of course, I want to be sophisticated, therefore I introduce the inner product between vectors, but this is the standard form. Okay. Now, what happens? You calculate the first variation of this action, of the action built using this Lagrange function, and you can distinguish in the Euler-Lagrange equations three addends. Because if you remember, we will go back to this very often. If you remember, we can define a Lagrangian operator, I call it square H of L. Okay, what is this animal? This animal is minus d over dt, dl over dq dot h, plus, you discover that somebody, the person who is talking with you is a true mathematical physicist if he uses minus here and plus there. This is a secret. Of course, if this is equal to 0, you can change the sign. But you get this integrating by part. So you have to write minus there. Okay, so I believe that Professor Marchioro was selecting me in a concorso 25 years ago because I wrote minus there. I'm nearly sure about this. Okay, so if you build this operator, so you give a Lagrangian, you build this operator, you get a given function in terms of q dot. Of course, you calculate everything along the motion, and you derive this over dt, and you get a given time function of time. Okay? Now, this operation is linear. So if L you split in terms of T, kinetic energy, minus internal potential energy, minus external potential energy, okay, then you can write the Euler-Lagrange condition of stationarity in this way. You can write this animal ht equal this animal hu int plus this animal hu x times delta qh times delta qh. Okay, then you can integrate with respect to time. So what you get, that your stationarity condition can be interpreted as follows. The work done by u int over delta qh, the work done by ux over delta qh equals the work done by inertia forces over delta qh. Okay? Now, violently, Maupertuis and then Hamilton were attacked by physicists who believed that least action principle was not suitable to be the foundation of all physics. This statement, in this moment I remember that Poisson claims that least action principle and any variational principle is useless, devoid of any physical meaning, and too abstract for being useful. Okay, so consider that these people, when they tried to give a general foundation of mechanics, they were violently attacked by other scientists who claimed that least action principle is not suitable for describing, for instance, dissipative phenomena. This misbelief is deeply rooted in the head of many persons because it is written everywhere. Okay. This statement is absolutely false. I will show you that, for instance, heat equation, the prototype of dissipative equation, can be deduced using a least action principle. However, there are deep, complicated, not completely understood mathematical points. So I may agree with Hamilton, Piola, Lagrange. Instead of talking about least action principle, one could slightly generalize. I repeat, maybe there is no generalization at all. So either we can embed least action principle in a more general frame so that we get dissipative phenomena included in the least action principle, then this is not a generalization. Or this embedding is not possible, then this principle I'm going to formulate for you now is actually a generalization of least action principle. Okay, so there is a slightly problematic point to be understood. nobody knows really if least action principle can produce every dissipative equation, every conceivable dissipative equation, because actually all dissipative equation was deduced with the least action principle. Okay? So, which is the trick used by Lagrange himself, by Piola, by Hamilton? Instead of stating that the motion is minimizing action, so instead of introducing one action functional, calculating its first variation and equating to zero this first variation on the motion, what are they doing? They say, okay, I postulate the existence of three linear functionals. W inertia, W internal actions, W external actions. Okay, they are functionals, linear functionals of the small variation of the motion, okay, and they are generic functionals depending on the motion. So here you have two arguments. You have motion, comma, delta Q. It is linear with respect to variation of motion, and it is generic in terms of motion. So instead of postulating one functional, the action functional, and then calculate its first variation, if you want to fight against Poisson, what you have to do? You have to introduce three linear functionals, which we can call work of inertia, work of internal actions, work of external actions. Okay? And the basic postulate of mechanics becomes that the first is equal to the sum of the seconds, of the third and the second and the third. What I've shown you, but we will look this in deeper detail, is that least action principle plus decomposition of Lagrangian in three terms implies the principle of virtual works, because this animal is called principle of virtual works. Okay? I said all this in a very general setting last time, at the end of my first lecture. Now you see that having calculated the Lagrange equation for a finite dimensional system, having in mind this simple example, you can easily understand why least action principle implies the principle of virtual works. Okay? However, there is another belief deeply rooted in the head of many persons. The belief is that this is true only for finite dimensional systems, which is not true. Okay, so before proceeding, of course, I have decided to show you something which falls in the declaration of the interest of a professor of Scienza delle Costruzioni, so nobody can be offended. Okay? This very strange Italian habit of dividing knowledge into parts, and I cannot teach fluids, unless a professor of fluid dynamics allows me to talk about it. And a professor of fluid dynamics cannot talk about the theory of Timoshenko beam, okay? Unless I allow him to do it, of course. Okay, this is a joke, but not so much, unfortunately. So the idea is that this point of view can be reproduced exactly for infinite dimensional models. Actually, in my opinion, the first evidence about the principle of virtual works or least action principle can be found in the books of Euler, where he applied it to the theory of beam. Of course, you can say that the principle of virtual works has an Hellenistic root, but I mean, the first time where you read about the principle of least action and virtual works is when studying infinite dimensional systems. So it is clear that this postulation is valid in general. But I want to be provocative, and before proceeding, I give you a small homework. So I wake up one morning and I give you this very simple Lagrangian for a one-dimensional system. The Lagrange coordinate is the variable x, the velocity is x dot. This is the Lagrangian. Apply this operator, you will discover a dissipative equation. You discover the spring mass damper, where this animal gives you an information about the friction coefficient. So even if I could be in serious difficulties, if you give to me a dissipative equation and you ask me which is the Lagrangian behind it, this simple statement says, this simple Lagrangian proves that it is not true that dissipative systems cannot be treated with a Lagrangian formalism. Okay. We will go back to this point many times. Okay. Now we go to the theory of beams, of Timoshenko beam. Of course, Timoshenko beam is something rather recent, but I adapt the reasoning of Euler for showing you the calculations. What I want to prove to you is that the reasoning we have done for finite dimensional Lagrangians can be generalized for infinite dimensional systems. Of course, I could start with the most general Lagrangian for infinite dimensional systems as done in Landau, and we will study it. I prefer to give you a simple example before. Okay? So you will be able to understand, hopefully, looking at something you should know already, or it is not so difficult to recover what I'm telling from what you already did, so that you have a clear idea that the procedure conceived by Lagrange is very general. La cinématique d'abord. So I want to study a very simple system. I have a beam made of a line which we can call middle line, and in every point of this middle line you have a section, which we may imagine to remain undeformed, rigidly deformed, or you can assume that this section changes its shape, but it remains always planar. Okay? Then, for making everything very simple, we assume that this mechanical system can move only in a plane, and every barycenter of every section moves transversally with respect to the shape of the average line in the reference configuration. So you have a displacement of the barycenter orthogonal to this line, and every section is rotating only around an axis which is orthogonal to the plane of the blackboard. So the kinematics of this system is very easily described by one scalar field U, S, and T, where S is the space variable along the line giving the reference configuration, and T is time. To this you have to add phi of S and T, this phi being the rotation of the section in the passage between the reference configuration and the actual configuration. So, if this is the shape of the beam after the deformation, in general, the section is not orthogonal to the actual configuration, even if it was orthogonal in the reference configuration. We will see that equations seem to be simpler, but it is not true, when you assume that this section remains always orthogonal. This is a simple example of modeling of a simple system which includes everything. The theory of partial differential equations of parabolic hyperbolic type, Lagrange multipliers, cutoff in the wave propagation. I mean, you have everything inside this very simple example. So I think it is worth that as an exercise, when describing the general theory, we stop to talk about this simple example. Okay? Of course, we will not do Piola transformation. So we will confuse reference configuration and actual configuration geometrically. So we will assume the so-called assumption of small deformations. So we assume that U prime and phi prime are very small together with U and phi. Okay? This is very elegant because this allows us, of course this means that the elongation, write the standard formula for finding the length of a curve. This curve has a parametric representation given by SUS. So if you write the square root integral of square root, which we have written last time for a perimeter, you discover that if epsilon is the order of magnitude of US, then the elongation of the curve is epsilon square. So the curve remains of the same length up to the first order. So in linearized theory, there is no relevant elongation. Okay? So this is a first very important observation. Then we have another very important observation. I hope that you will not be frightened when I tell you that the tangent curve to the actual shape in a given point, the tangent line, so let us call this psi, is such that tangent of psi is equal to u prime. By the way, this is a standard geometric argument you find in Euler treatment of the theory of beam. Okay. So when you calculate the derivative of u, you get the tangent of this angle. The tangent of this angle is called tangent of that angle because it refers to the tangent curve. I mean, this is not a way for confusing, okay? Now, if you assume that this tangent is very small, this is sinus over cosinus, I will not offend you. If you write the Taylor expansion of the tangent of psi close to psi equal to 0, you get psi plus infinitesimals of higher order. Okay? As you are not student of environmental engineering, you are not allowed to say that this is too advanced mathematics. Okay? Now, which is the, now I can show you, I could do it with a Cartesian formula very easily, but I want to let you have the flavor of the reasoning of Euler. Then Euler discovers that if you have two straight lines which are respectively orthogonal to two other straight lines, then psi, the angle formed by the first two straight lines, is equal to the angle formed by the second straight lines. Okay? So if I consider the orthogonal direction of the tangent line, I know the drawing is very bad. Then I have the parallel displacement of the section from the reference configuration to the actual one. Then this angle is psi. Okay? However, the section has been rotated by phi. So I can introduce so-called shear deformation of my beam. Shear deformation is the defect of orthogonality of the section in the actual configuration, of course, when the shape of the average line is known. Now, for historical reasons, engineers built until wings of airplanes only beams which are unshearable. But this is not, you have to learn about this. As they did not know how to study shearable beams, then they conceived only unshearable beams. So you cannot tell that studying shearable beams is useless because it is not practical. actually, what engineers are doing, which is very wise, they refrain from conceiving something which they cannot control with mathematics. So actually, the mathematical knowledge in a given moment gives you a limit of engineering applications. When Timoshenko introduced this more careful description of beams and beam deformation, he could design airplane wings, which is a rather important technological advancement. So, which is the deformation we are considering, we are dealing with? We have phi prime, which is the bending deformation. So you have an infinitesimal part of this beam, which now I am magnifying. So this is the section, this is the closed section. Okay, and this is deformed in this way. So you have phi s plus ds minus phi of s. You divide times ds, you get phi prime. So phi prime is a particular measure of deformation. Phi prime gives you bending deformation. And the other deformation measure is given by u prime minus phi. This is shear deformation. We have ended our kinematics. Why? Because now we simply go to Hamilton and we ask him, which is the Lagrangian U conjecture for this system? The answer is the following: kinetic energy minus potential energy. Kinetic energy is very easy. 1/2 of rho, I write only one time rho of S, because the mass per unit line in principle can vary. Okay, before you start telling it is too abstract, think about the wings of an airplane and you understand that mass density is varying in that case. This times u dot square. This is the kinetic energy related to displacement. Then you have plus 1/2 j t phi dot square. Now I am using something of the theory of rigid bodies. When you have a rigid body which is rotating with a given angular velocity, the kinetic energy is given by the moment of inertia times the square of the angular velocity. Okay? You have to think why Euler, before studying this, studied the equation of a rigid body. Okay, there is a logics behind. Okay? Then, so this is the kinetic energy we have. Then we have to find the internal energy. Okay, we are like hook. For every deformation measure, we introduce a quadratic deformation energy. So we have 1/2 of a rigidity k times theta phi prime square, which is the deformation energy hidden in this deformation mode. And then you have plus 1/2 chi t, so this is the shear modulus, times u primes minus phi square. Okay? Then you have external energy. We assume to have dead loads. What is a dead load? A dead load is very simple. It is an interaction with external world which is linear with respect to displacements. This means that a given set of material particles see always the same external force, independently of its configuration, actual configuration. So, although we could write, I need to be very careful for the sign, so although we could write more general, I will write Bu minus mu theta. Why minus? Phi, yeah, because I was very stupid. I wrote here theta and I told you phi. Okay, so we have to understand what this means. This means that for a displacement u in the positive, of course I didn't tell you, but I have to tell you that my reference is this one. So all my vectors are projected along this reference, okay? So when you apply B, if the displacement is in the same direction of B, your potential energy decreases, and if U is in the opposite direction with respect to B, your potential energy increases, okay? So this minus sign cannot be removed unless you are crazy, but this happens. There are true engineers who are projecting forces along minus E2 and displacements along E2, so that they get rid of the minus here. When I was a young ricercatore in '92, a delegation of engineers from the province of Latina came to see me for explaining me that a true engineer is writing plus here, and that I was not teaching true engineering theories because I was using minus there. So I needed to explain them, but I don't know if they managed to understand that I find a little bit twisted to project forces along minus E2 and displacement along E2. Of course you can do it, it is possible. But this doesn't mean you are engineer. This means that you are twisted, in my opinion. But it is a question of tastes. Okay? Now we have our Lagrangian. Remark that we have two integrals to be done, because we have the density of action with respect to length, and then we have the density of Lagrangian with respect to time. So differently from what we have done before material particles had a label belonging to n. So you had a discrete number of labels. Now you have a continuum of labels. So as Piola clearly understood, instead of writing summations, you can write integrals. So our least action principle reads as follows. You will see that this example gives us a lot of understanding of what is done, why it is done in that way or another. You have to calculate the integral with respect to ds and then the integral with respect to dt. So you have to minimize this functional. Okay? Now, we have to do some calculations. I have written here, in order to avoid to use the wrong minus sign in the deduction. Okay? So, what we have to do? The motion is phi of s and t, u of s and t. You have to add a small variation. So you have plus delta phi of s and t plus delta u of s and t. So even if you do not know anything about Frechet differentials, Sobolev space, Banach space, you behave like a young Lagrange, end of 18th century. You take this in the action, then you subtract the action estimated in phi and u, you neglect infinitesimal of higher order, and you get some equations. We will discover that these are exactly the equations you have studied while studying the theory of beam. Okay, now I do calculations a little bit quicker, but you will discover that what we have done for finite dimensional systems is helping us a lot. So I start with the first variation of integral between t0, tf, integral between 0 and L of 1/2 rho u dot square. And I don't write ts dt. Okay? So this is equal to integral t0 tf integral 0L of what? 1/2 rho u dot plus delta u dot square minus 1/2 rho u dot square. Of course I could, and we will do in a more general way this calculation. But in this moment, what we know, we can develop this square. This minus that goes away. Delta u dot square is infinitesimal of higher order. Then I'm left with the double product. So I kill 1/2 and I have this animal. Okay, now you have to think that for us, maybe this is easy. But when Lagrange was doing this calculation, the theory of integration was at the very beginning. So it was very painful for him to apply Fubini theorem and invert the order of integration here. Okay? So you can write this like that. And you can integrate by parts in time this animal. And you can formulate your least action principle as follows. Motion is stationary for isochronic motions. So when you have the same state at T0 and Tf, so the set of motions among which you look for your stationary motion is the set of motions which has a given configuration at T0 and another given configuration at Tf. Okay, this is very useful. Why? Because you discover immediately that this animal, I write here, you discover immediately that this animal is equal to, I have to write the integral here. So you have rho u dot delta u dot minus rho u second delta u. This reasoning is not trivial. This reasoning was done first by Lagrange. This was called the theorem of alive forces. This animal you can estimate at T0 and Tf. Delta u is 0 here and there. So this animal dies, and you discover that the first variation of kinetic energy is equal to the work of inertia forces. This is not physics. This is a mathematical theorem. So you can decide to wake up one morning and choose the Lagrangian, or you have to decide that inertia as a functional work, the functional giving you the work of inertia forces has this form. Frankly, it seems to me that it is easier to accept that in general we are dealing with kinetic energy. Okay? So the first variation of the first part of T, kinetic energy, we have estimated, and it is minus rho u double dot times delta u. Okay, I will not repeat the calculation because it is exactly the same for the second term. This second variation is minus j phi double dot. So the corresponding functional to this is minus rho u double dot delta u. The corresponding here is minus j phi double dot delta phi. Okay. Lagrange says that when you accept least action principle, you postulate Lagrangian, then everything is plain calculation. So you do not need to think anymore. You need to estimate first variations. Okay? Now you will see how elegant is the deduction of the first variation of this, and how we can elegantly interpret it. So I write here of course the first variation of this animal is very easy. What is the derivative of a linear function? The linear function itself. This is true also for functionals. Okay, so the first variation of this animal I will not calculate. Okay. Now we have to calculate the first variation of this animal. I cannot split it because you have theta, of course it is phi, you have phi appearing everywhere. So this animal has to be calculated all together. Moreover, now the integration by parts is not with respect to time. It is with respect to space. So when we will have the integration by parts done, we will discover some boundary terms. Okay? We will talk about these boundary terms at the end. Okay? So this is equal to you know what? Time we don't need to consider because there is no time derivative here. So this animal we will write at the end if needed. Okay? Okay. So we have integral Km phi prime delta phi prime plus kt u prime minus phi delta u prime minus delta phi. They are quadratic terms, so the first variation we have learned how to calculate. Then I attack this animal. So I try to write everything in the appropriate way. So we have Km phi prime delta phi, everything prime, minus Km phi second delta phi. This is this first term. Okay, then we have this times that. So I have minus kt u prime minus phi prime delta u. Okay, and here I have kt u prime minus phi delta u prime. Because you derive this, you get this animal and that animal. So with the minus sign, you get the right. And with the integration by parts, we have done, because you have plus kt u prime minus phi delta phi. Wait a no, I'm using plus plus here.
No, but there you have minus delta phi, right?
Here?
That you have to
Sì, sì. Okay. Now the big problem is that I've written everything with plus here, while in Lagrangian you have kinetic energy minus internal energy. Okay? So it is for this reason which I wrote this on a sheet of paper before, because I want now to avoid to use the wrong sign and then lose all the effect of this deduction. So you can consider the dual in work of delta phi. What is the dual in work of delta phi? Everything which is multiplied times delta phi. We will deal with these two terms later. So let us start writing the equations, so-called bulk equations. Okay, so what you have is Km phi second plus Kt u prime minus phi plus mu, which comes from here when you have played suitably with the signs, and then you have minus j theta phi second. This animal appears times delta phi, and you have two integrals in front of it. Okay? Then you have this animal times delta u. Then you have some boundary conditions which we will discuss later. Something happens at the boundary we discuss later. Okay? Now that magic theorem by Lagrange, which we have discussed already, applies another time. You have an arbitrary function delta u and an arbitrary function delta phi. So for instance, you kill delta phi, you kill delta u at the boundaries, and you consider only a test function suitably continuous. Inside, what you get is that this animal is equal to 0. So the dual in the work, in the expression of total work, the dual of the infinitesimal variation of delta u is 0. The same applies for the dual of delta phi. So you have two partial differential equations for your unknown fields. Of course, you can decide that you give initial conditions, which is the standard trick when you have isochronic motions. Okay, so you give phi of s and 0 equal something, and the same for phi dot for u and u dot. You give initial conditions. But in order to have well-posed problems, you need to give boundary conditions. But the method is giving them to you easily. Now we see how. The first variation of action, once you accept these bulk equations, reduces to this first variation. So this has to be 0, or you are missing something if this is not 0. So we try to understand from these boundary values which other external actions are admissible. What is powerful in this method is that it tells you which are the admissible external actions. So here we postulated only a potential energy related to the bulk of your system. So you have a potential energy which you are expressing in terms of integrals. And indeed you introduced a force per unit line, B, and a couple per unit line. Now, after this integration by parts, you discover that Km phi prime delta phi 0L plus Kt u prime minus phi delta u 0L, these are fields estimated at the boundaries in 0 and L, and the value of these quantities must vanish for every admissible delta phi and delta u. The simple thing is I assume delta u 0 in both sides, and these two animals become 0. What you are doing? You are obliging to your beam to remain clamped. In 0 you have no displacement, in L you have no displacement, in 0 you have no rotation, in L you have no rotation. This is very well possible. I mean, you can consider this case. But what if the right boundary is free? If the right boundary is free, then delta phi of L is arbitrary and delta u of L is arbitrary. Nothing bad. This animal has to be equal to 0 for every admissible delta phi and every admissible delta u. So what you have? You have Km phi prime in L times delta phi L equal 0 for every L, for every delta phi. Now, Lagrange was very careful. He proved that for every interval, you can choose a function which is 0 everywhere except in L. So he was very clever in finding also this function. So he could prove that you can choose a sequence of delta phi such that in the limit, assuming that this is equal to 0, implies that this animal is equal to 0. This is one of the three extrema boundary conditions. Similarly, you get that kt u prime minus phi in L is equal to 0. So these are the two boundary conditions to be added. Of course, as on the left you have clamped section, you add u0 equals 0 and phi 0 equal 0. Which is the order of of course I have missed something here. Because when integrating by parts, I had the derivative of this animal. Okay? I tell you why I have discovered it now. This is crucial. This is, mistakes you can do all the time, but you have to activate a feedback control of what you are doing. You have 4 boundary conditions. Assume that there is no motion. You want to study equilibrium. This is a second order ordinary differential equation. This is a second order ordinary differential equations with respect to space. How many constants of integration do you need? 4. Here, the 4 boundary conditions needed for finding the 4 integration constants. But the story is not yet ended. Why? Because when you look at this boundary condition, these boundary terms, you decide that you can introduce ux concentrated. For instance, you can decide that you have 1/2 of gamma u of L square. This is a spring here. You have a concentrated potential energy which is related to this displacement. Why you decide that this is admissible? You decide that this is admissible because when you estimate the first variation of this animal, you get gamma times u L delta u L, which sums up with what you have here, and here you get plus gamma UL equals 0, which is a well-posed boundary problem. So we will come back to this. The power of this method is the following. Once you have postulated a part of the Lagrangian, then you know which are the admissible external actions which your system can sustain. Because everything you have in the first variation of your internal energy, every term in your first variation can be added to a suitable other term in external potential energy. So not only you have forces per unit line, couples per unit line, but you can have concentrated forces, concentrated couples. Okay? So calculating the first variation of Timoshenko beam, not only you discover the evolution equations, the boundary conditions which are suitable, but you also discover which are the applicable external actions to your system in the framework of your model. Now we are tired, but we cannot stop here because we need to go into a strange story. It is the story of what Navier decided to teach à l'École Polytechnique of this theory. Navier decided that it was too complicated. So he decided to formulate a theory more physically reasonable. Okay, so what he did? He looked at this animal and he said, this animal is the dual of rotations. What is the dual of rotation in the theory of Euler rigid body? A momentum of forces. So he wrote M equal Km phi prime. Up to now it is only a name. You are free to give names. Then he looked at this animal and he said, what is this animal? It is the dual of a displacement. So I call it shear force, T. Why shear? Because if you imagine to cut here your beam, this is a force in this direction. So it is parallel to the imaginary cut in two different parts of your beam. So he called this T equal KT U prime minus phi. Okay? And he decided, this is a mystery. It is a psychological mystery. Because why M and T are more physically understandable than U and phi? Engineers claim that contact actions, because these are a particular class of contact actions, are more practical. Nobody measures contact actions. Are you cutting a beam halfway and measuring the force needed for keeping the half you have left in its place? What are you measuring? U prime, theta. deformations you are measuring. We are only measuring deformations. But look how clever is Navier. Bam! T prime minus rho u double dot plus b equals 0. Balance of force for the infinitesimal element of your beam. And I postulate it. So I wake up one morning and I postulate it. Then this animal is what? This animal is m prime plus t plus mu minus j phi dot equals 0. Balance of couples or moment of forces. Then I add this constitutive equation and this other constitutive equation, and I have closed my theory. This is the typical a posteriori decision. You already know the solution and you pretend you are finding it. This phenomenon has been described very well in the literature. I advise you to read the wonderful book by Lucio Russo, The Forgotten Revolution. It is amusing. Niccolò Tartaglia was pretending to be able to read Greek. He had an ancient translation of Archimedes from Greek to Latin, written by M&MoCS, who couldn't understand mathematics. So it was a word-by-word translation. Okay? Tartaglia corrected Archimedes and writes a book whose title is Nicolaus Copernicus correcting the book, The Mistakes of Archimedes. Now we have the original text in Greek, and we have discovered that actually Tartaglia misunderstood nearly 20% of Archimedes' results. Archimedes was right, and Tartaglia did not understand what he was reading. I am afraid that the poor Navier did not understand Euler, and he decided to correct him. Now, why this has to be said here? You are learning how to become a scientist. So your work in principle should be to invent new equations for describing new phenomena. When I was more or less old as you are now, unfortunately for me, this is the only weak point of my studies, I believed in the postulation framework of balance laws. So I believed that a theory was easily founded by postulating a suitable set of balance laws. Now, what is the big problem? If you have a conservative system, you want the conservation of mechanical energy. So imagine that you wake up one morning, you write balance of force, balance of momentum, then nobody tells you which are the good constitutive equations, you write some constitutive equations. You will never find conservation of energy. Why? Because this is the dual in rotation, and this is the dual in displacement of a given derivative in generalized sense obtained from an action. If you wake up one morning and you write balance equations and constitutive equations without being guided by the right action, you will never find a linear functional which is the first variation of something. If I give you a vector field V, randomly, do you have any chance it is the gradient of something? This is a field made of 3 scalar components in R3, and the potential is 1 scalar field. So you will never be able to produce every triples of fields starting from one field. Helmholtz understood this very well when he found the decomposition of V in the 2 parts. The one which is the gradient of something, the other one which is the rotation of something else. Okay? Now we are in a much more general framework. You are infinite dimensional configuration spaces. So you are not living in R3. You are living in a Sobolev space. You postulate some balance equations and you want it is the first variation of something. It will never happen. So I have lost 2 years of my life postulating balance equations and constitutive equations. Then I decided that I was not clever enough, and I started to read French books where the solution of my problem was very easily obtained. Of course, if you want dissipation, we have to add some terms and you have to generalize our postulation process. This has been done by Hamilton and Rayleigh. So what we will do, resume of what we said now. I tried to give you a general idea of the postulation process a la Lagrange. Okay? Then I wrote for you Lagrange equations for a finite dimensional system, deducing it rather rigorously. I tell rather because we are not using functional analysis, we are using the first, second analysis, mathematical analysis in tools. Okay. So we are not finding the right norms, we are not doing everything in the most precise way, but I think it is precise enough. Then today, in order to answer to a question of Professor Casciola, I decided to give you 2 examples and to discuss with you the functional of kinetic energy, internal potential energy.